For this session, we have collaboration between Subbu in the US and Sakshi in India. They're going to both giving us this presentation.
Thanks, Josh, for the intro. Hello, everyone. Good morning, good afternoon, good evening to everyone. Hope everyone stays safe and healthy. Today, we are presenting about Kafka at Chegg. Who are we? I am Saravanan. I go with Subbu as a nickname. And I have my teammate Sakshi, and we both are from personalization platform at Chegg. Today, we'll be covering this in our agenda. What is knowledge graph? What is Kafka? Why Kafka? What are some of the best practices? And what's the future work in progress at Chegg? Knowledge graph. I want you to walk through a little bit on what use case we are solving and how Kafka fits our ecosystem. We are building a system called knowledge graph. We started this journey almost 2 years back. So what is knowledge graph? Chegg, as a student-first platform, offers various products like textbook solutions, study pack, experts help, tutoring, flashcards, practice exam, etc. So we build a system by ingesting different Chegg entities as listed on the left-hand side orange boxes, coming in as events in the near real time and getting ingested as nodes and relationships into knowledge graph. We use AWS Neptune graph database as the underlying data store to store this knowledge graph. Let's take a look at how an event really looks like. In this scenario, a student has posted a question, what is organic chemistry? How does it apply in the real world? This event will be stored in the source of truth system, here the question service, and they emit an event indicating this content lifecycle change. Events are produced in the JSON format and they comply with a cloud event specification. Cloud event spec is like defines a standard of way of defining the schemas, and it was also fairly new when we started our journey, and we are one of the early adopters. So let's take a look at what happens after the event is being produced. So the student posts a question and the question service emits an event. So events are published to Kafka and we have a service which listens to it. What does this service do? So the service listens to the events that is being produced and we do some event enrichment like transforming some of the interested properties that are present in that event and push it further down the ingestion pipeline, which lands as question nodes or deck nodes into knowledge graph. For the same event, we pick some other interesting information like question text here, what is organic chemistry, and pass it on to our data science APIs, where we have our trained machine learning models to predict more information about this event. In this case, based on the question text, the data science API could classify that this question belongs to this course, and also this question is related to this topic, and so on. We enrich those information further and create those predicted relationships into knowledge graph. So where does knowledge graph really help us? It helps us to serve very different use cases like experts routing. When a student posts a question, we know who is the best expert it should be routed to. And then of course, on the personalized recommendations, personalized marketing, etc. Let's take a look at what is Kafka. If you look for Kafka on Apache's site, this is how Apache has described Kafka and what it is and how it works. Apache Kafka is a publish subscribe messaging rethought as a distributed commit log. You have producers or publishers producing messages to the topic, and then you have subscribers or consumers consuming those messages. You can think of commit log as like a simplest storage abstraction. It is an append only, totally ordered sequence of records ordered by time. Let's take a look at some of the internals of Kafka. Kafka has various components. It has producers, it has consumers, topics, partitions, brokers, and a zookeeper. Let's take a look at each one of those. Kafka cluster has one or more brokers. So the recommendation is to have minimum of 3 brokers for high availability. So what are brokers? Brokers are the nodes that actually holds the data. Let's take a look at Zookeeper. Kafka is a distributed system, and it uses Zookeeper for coordination and to track the status of this broker nodes. Data such as the location of the partitions and the configuration of the topics are stored outside of Kafka itself in a separate Zookeeper cluster. Producers. Producers publish the data into a logical unit called topics. Each record lands in a particular partition within a topic. What is a topic? Topic is again a logical entity which has number of partitions. While we create a topic, we define the number of partitions and the replication factor depending on the use cases. Let's take a look at how the partitions layout look like. If you see this picture, this topic has 4 partitions created. The data in each partition is ordered by time from oldest to the newest data. When the data is produced from producers, it lands into different partitions based on the partition key chosen. There are many algorithms available to calculate this partition ID. The default and simplest is using the hashing-based partition. Let's take a look at consumer group. All the consumer instances with the same ID are grouped logically as consumer group. Each consumer within the consumer group will read from a selected set of partitions depending on the number of consumers available. Let's take a look at this picture. For the first one, the consumer group 1, each consumer is assigned a single partition, whereas in the consumer group 2, each consumer is assigned 2 partitions each. There will not be any overlap of multiple consumers reading from the same partition. We talked about the use case in the previous slides, and to efficiently build this knowledge graph, we need an infrastructure and technology which should support these massive features. Let's look at why Kafka. Scalability. Our first challenge was to scale at masses. We wanted to support ingestions to handle a scale of millions of data in real time. We wanted a streaming system which can produce millions of data per second and consumers consuming from it. Multiple consumers. We wanted a technology that supports the same message to be consumed multiple times for various different use cases. Replay mechanism. Systems are bound to break, and when they come back, we should be able to replay events to reconstruct the system at any point in time. Ordering. We wanted the order of the related events to be preserved. For example, when we wanted all the events related to a question being created, updated, or deleted should arrive to us in the same order as they are being produced. Retention. We are looking for a system which should provide configurable way to hold the data to our needs. Maintenance. And of course, we wanted a technology with very easy maintenance. We are AWS shop, and so the clear winner for us is using AWS MSK, which is nothing but managed streams for Kafka, and it's a fully managed service. Now, Sakshi will take you to some of the best practices we follow.
Yeah, thank you, Subbu, for setting the context. So hello everyone, I'm Sakshi and I'll be walking through over the best practices in Kafka which we are using in Chegg with the main focus on like scalability, like how to achieve scale in Kafka using best practices and how we handle error cases scenario in Chegg and in like Kafka. I will be talking about different monitoring, monitoring metrics, different tools which we can use, and how we can make use of AWS alarms for monitoring, and also how we can tweak different configurations to make the best use of Kafka for our like applications. Okay, so our first area is like scalability. So for that, I would like to explain how parallelism work in Kafka. So like the different, a record can be produced by a producer. It can land in any of the partitions. These partitions, they are lying over a topic has multiple partitions, and the multiple partitions are lying over can lie over multiple machines, and these partitions, they are listened by multiple consumers in parallel. And for example, here my topic has 3 partitions, and consumer group A has 4 consumer instances bound to it, and consumer B has 2 consumer instances bound to it. The maximum number of consumer instances which can belonging to a consumer group which can listen from a topic is equal to the number of partitions. So here, even though 4 consumer instances are there, but at a time only 3 consumer instances are able to read from my topic here. And so maximum parallelism here is 3 for consumer group A. And similarly for consumer group B, there are 2 consumer instances. So at a time, only these 2 consumers are reading from these 3 partitions from this topic. With this, I come with the first practice, that is the number of partitions. We should come up with the right number of partitions. We can decide the number of partitions based on the throughput and parallelism we want to achieve. And for a topic, once we increase the number of partitions, we cannot reduce it again. So that's also we should consider. Then coming with the number of instances within a consumer group. So as you see, scalability and parallelism, they are determined by the number of partitions which are being consumed in parallel. We can, for example, in our team also, we have a main topic which has 50 as the number of partitions, and there is a consumer service which is listening from my main topic, and we have set the scaling policy from 12 consumer instances to 50 consumer instances. So in case of average load, my 12 consumer instances are reading through those 50 partitions, and in case of maximum peak load, all the 50 partitions are being read by the 50 consumer instances of the of my consumer service for maximum parallelism. Then I'm going to discuss about partition key again, a very important aspect. And so events, as Subbu mentioned, events in Kafka are ordered, but Kafka, to ensure the ordering of the events, they should land in the same partition. So there, we are using hashing as the partitioning strategy. So for example, there are different question events which are arriving to our Kafka topic from different teams. So we have question ID as the partition key, be it a create question event, update question event, or delete question event. So this ensures all the events belonging to that particular question ID will land in the same partition, and they will arrive to us in the same order as they are fired, so that we can also consume them in an ordered way. Now coming to the retention period, we should decide the retention time period based on our use cases, how long we want events to be stored, or how long if there is any requirement, whether we want to replay the data if needed. So this is again important, because Kafka works on this. The cost of Kafka usage, or MSK usage, also is determined by the log disk usage. So if there is more data, the cost, costing, it can impact costing. Okay, coming to the next area, error handling. For event error handling, we have created like a central library. So the idea here is the consumer, it will be reading from the main topic. So either it will be a successful flow, or there can be a validation error or a retrieval error. So whenever there is a validation error, for example, if some important information is missing, then then our central library publishes those events in the validation DLT topic. And if there is any retrieval error, suppose during processing the service which we are calling, it gives 503 error, then we can push that event, then the library pushes that event in retry topic. So we have a mechanism where the consumer, it can listen from the retry topic, and we can also configure how many times we want to retry for a particular consumer, how many times we want to retry on the retry topic. So the consumer will be retrying the configurable number of time after an exponential back of time period. So if in the retry attempt, the processing goes successful, then it will be like the flow will be completed. But still, if the error is coming, then the library publishes it into the service failure DLT topic. The third area, which is the monitoring. So for understanding monitoring, we should understand the important AWS metrics also, which AWS is providing us and which we are using extensively. So there are metrics which are available at per broker level, per topic level, and also at the partition level. For example, broker level. So this is the first one, and it is very important for us. Kafka app log disk use. So it tells what is the percentage of disk which has been used for our Kafka cluster. So for example, here in our team also we have kept the threshold to 80%. So if the disk usage exceeds 80%, then we fire an alarm and we can take the respective action on this. Then under min ISR partition count. So this tells about the replicas which are in sync within a partition. So we have 3 replicas for a partition. So we need at least 2 replicas to be in sync with each other at all the time. So we have set the value to 2. So similarly, for under replicated partitions, again, this is one of the important metric which AWS also recommends. So this should not be greater than 0. So if it is greater than 0, it means we have not right sized our cluster, or there is some ACL which is blocking the traffic. Then active controller count. So active controller count should also be 1. It represents how many, it represents that one controller per cluster should be active at a given time. Then there is then I'm going to for the topic level. So messages in per second. Messages in per second, it's self-explanatory. So this can be configured both at topic level and broker level to keep how many messages are being produced for a given topic. Similarly, there is messages out per second as well to understand how many are consumed. Then we have these 2 new metrics. These 2 metrics are introduced recently. These are present per partition level for a consumer group. So offset lag, this will tell how much consumer lag is there per partition for a consumer, and maximum offset lag will tell the sum of the consumer group lag across partition. I'll be discussing about these 2 in detail in the coming slides. Now I'm going to discuss about the different tools which we are using in Chegg. So there are many open source tools available for Kafka. We also explored some of them: Kafka Burrow, Kafka. Then there are open source tools which Confluent also provide, like KSQL, Kafka Cat. So we are using Kafka extensively. So CarpDrop is a web UI tool. So we can see here how many Kafka brokers are there. And if we click on a particular topic, we can also see how many topics are there for a particular cluster. So if we go on a particular topic, we can also see how many consumer groups are listening to that particular topic, and we can also see a particular message at a particular partition level or at a particular partition or at a particular offset also. And we can also like create a new topic. So this open source tool is written in Spring Boot and is present as an open source Docker image. So we are using the open source Docker image of it. Then auto scaling policy based on the consumer lag. So to understand, let's first go through what consumer lag is. So as Subbu described in earlier slides, so the producer will be, this is a partition of a topic, and producer will be writing from like left to right. So here the producer has written till the index 12. The consumer group A has read the messages till offset 9. So, and consumer B has read the message till offset 11, index 11. So, so the consumer lag for consumer A here is 3, and for consumer B, the consumer lag is 1. The higher the consumer lag, it indicates there is a higher difference between the producing rate and the consuming rate. So this can also indicate slowness. Then so with respect to consumer lag, the AWS has provided us a new metric, which is the sum offset lag. It is the sum of the offset lag for a consumer group across all the partitions in the topic. So if it reaches a particular threshold, then we can decide whether we need to auto scale. So here in this diagram also, we have set in our service, we have set an alarm which so whenever we see that the consumer offset lag has exceeded a particular limit, for example, it has exceeded 51,000 messages, so then we trigger an alarm. So this alarm in turn calls the auto scaling policy. So it can scale out my services, like it can further increase the number of consumer service instances. So, and this is a very new feature. So it is all available only in the latest version of MSK. For older version, the AWS team is still working to provide the support. Then we have alarms at broker level and like topic level. For example, like we have put alarms on the validation DLT and retrieval and service failure DLT topic also. So if my number of messages exceed a particular threshold, then it means something is not right in my application. I am seeing a higher error rate. So those kind of alarms we can also keep based on these metrics. Then there is a integration of CloudWatch metrics and New Relic. So we can also create dashboards on New Relic to view all the metrics at one place. Okay. So the last one, like sometimes we run in the different conditions that my consumer is reading the same message again and again. It is not committing the offset, or my current situation when my application is restarting, it is just replaying all the topics from all the events from the beginning. It is consuming all the previous messages. So what can be the situation, but why the situation is how to config, how to tweak the configs here. So like Kafka consumer, they can commit offset automatically by default, and so this is the property which does enable auto commit. So it means the Kafka will be committing the messages within this time period. So if our consumer is not able to process the message within this time period, then it will not be able to commit. So instead of instead of Kafka committing itself within scheduled time, if you want to commit manually commit yourself, once the consumer processing has been completed, then we can disable this property. We can set it to false to take the control over committing the Kafka offset messages. Then there is another property like auto offset reset. The earliest and the latest value of the auto offset reset property is used when a consumer, so whenever a consumer restarts or there is a consumer group rebalancing, and there is no committed offset of the signed partition. In this case, we can choose whether we want to reread the messages from the earliest offset available or from the latest offset available. Yeah. So over to you, Subbu, for the work in progress. Yeah.
Thanks, Sakshi. So what's something that's been happening at Chegg for the future state? So we are working on switching from the JSON to Avro. So I just mentioned earlier, like all the events currently are produced in the JSON format. So why we need to switch to Avro? So it gives an ability to validate the data produced against a schema. So, and it also stores the data in a very compact format, which helps us in saving a lot of storage space. So that's the first change we're working on. The next upcoming work is like switching to the latest cloud event spec. As I mentioned, all the events produced from our producers on the source of truth system follow the cloud event spec, which provides a consistent way of defining events. So the cloud event spec is also evolving in parallel, bringing in more standard to the schema definition. And of course, we are building the personalized recommendations using KSQL DB. So what we are doing there is based on the student's engagement history with the Chegg portal, we recommend a lot of personalized content to the students. Having said that, I open up the floor for questions.
One quick question for you, Subbu. It's a great presentation, both of you. Can you describe a little bit more on the cloud event spec?
Yeah, so the cloud event spec defines a standard way of defining the schemas. So currently with the JSON format, so what it does is it gives the ability to validate a schema. Like you can define a schema definition, like this is how the producer produces an event. You should follow the standard structure. So it tries to validate, we register the schema against the registry, which holds like a central repository of maintaining all your schema definitions. So whenever you produce the data, it gets validated against the schema present in the registry. And you get upfront validation errors saying something goes off when you're producing the data, which is not conforming to the schema.
So is this Chegg specific or?
No, it's not. It's industry specific. It's evolving. It's not just Chegg specific. Yeah.
Another question, if there are no other questions from anyone else. What challenges you see, what challenges or benefits you see between MSK and managing your own cluster, Kafka cluster?
Oh, obviously, in terms of anything maintaining the infrastructure, right? So if you want to maintain your own, you need to have a dedicated team. And then you need to make sure when to auto scale the storage, when to auto scale the broker nodes, whatnot, right? So since MSK from AWS is a fully managed service, they take care of all the heavy lifting for us. So
one more question by Raghavendra. Any reason for changing from JSON to Avro?
Yeah, so the main reason is with the plain JSON, we don't get way to validate against the schema, as I said. And the other one is in terms of saving the storage space. When you are sending a lot of events, in JSON format occupies a lot of storage space internally, but Avro is kind of serialized in a fashion which is stored in a binary format internally. So it is more compact than JSON.
How are we looking, Ankit? Do we have time for any more questions?
We are right on time.